The laboratory experiment consists of the synthesis of alum from elemental aluminum metal. The steps that were followed to do so were the following. The first reaction involves the production of a solution of aluminum and potassium hydroxide. Since aluminum is a reactive metal with reactivity greater than that of hydrogen, it will form AlOH minus aluminum hydroxide. Next, the solution, which is of a dark brown colored, was filtered using a vacuum to remove any impurities. This is essential to optimizing the process of recrystallization, as impurities disrupt the formation of the crystal structure due to the differences in identity and chemical properties. The filtrate appeared to be clearer in color than the solution being filtered. Aluminum hydroxide is an amphoteric species, meaning it can react with both acids and bases. This property is demonstrated as the addition of sulfuric acid to the newly formed solution leads to the formation of AlOH3 precipitate. This is due to the limited solubility of alum under experimental conditions. When the acid was added, the formation of a white foam-like substance was observed. However, after stirring, it dissolved back into a clear solution. To dissolve the precipitate, add more acid that will neutralize the aluminum hydroxide precipitate, all together using a hot plate and a magnetic stirrer to speed up the dissolution of the ions in the solution. The reason behind the correlational relationship between an increase of temperature and movement with an increase of the solution is that the kinetic energy provided by these means aids the overcoming of the potential energy required to break the ionic bonds between the aluminum and hydroxide ions, or in other words, overcoming the lattice energy, and forming dissolved ions in solution. Next, temperature is employed again, but this time it is done so through an ice bath to decrease the temperature, thus decreasing the solubility. The temperature decreased through the placement of the solution in an ice bath. In this manner, the solubility of the alum is decreased, and the precipitate will form. The next step involves rinsing the alum in order to remove any impurities. Impurities disrupts the recrystallization process as it disrupts the geometric lattice structures of crystals. To do so, a solution of 50-50 ethanol-water mixture is employed. The reason behind this choice is that the water will lead to the dissolution of the alum crystals, which appear to be of a white color. In order to avoid this, ethanol, a nonpolar compound, will reduce the ability of alum to dissolve in the solution, thus effectively removing the impurities from the solution. In order to separate the solution from the alum, vacuum filtration was employed. Lastly, a saturated solution of alum was formed by weighing out the mass that will lead to a saturated 40 ml solution when added to distilled water. This number corresponded to 5.64 grams according to the following calculations. The solution was distributed into vials and taken home to observe. The crystals do not appear to have formed so far. This is considerable as the experiment was performed on Wednesday afternoon, 2 days prior. In other words, it can be inferred that nucleation, the time required before the solution can start transforming itself into a crystal, is still ongoing. The ions are still positioning themselves to form a crystalline geometry. In terms of sodium chloride, a method of recrystallization is dissolving table salt in distilled water in order to form a saturated solution. To do this, stir the salt into boiling water until no more dissolves. Next, place a piece of cardboard into the solution until it appears soggy, and place it underneath the sun. As time will pass by, the water will evaporate and recrystallization will occur. To form a larger, more geometrically perfect crystal, there is another method. Form a supersaturated solution of dissolved NaCl and water into a watch glass. As the water evaporates, collect one of the smaller formed crystals and attach it to a string that can be held above a beaker with a supersaturated solution of NaCl. It is important for the solution to be supersaturated so that the crystal does not dissolve and NaCl clumps on the sides of the crystal. With time, a larger crystal will start growing. This can be done more effectively in a cooler setting with less lighting in order for the process not to be disturbed.